Okay, hi everyone in YouTube and here present in the live section. And today I will continue in the last lecture that is about the quantum simple harmonic oscillator, and means the continuation on the last section. So let me share my things. Today I don't have so many slides because it's just to when I producing the PDF files in the whiteboard, it's just to you guys know that we are in the second part of the harmonic oscillator. So the idea is continuing the quantization of the single harmonic oscillator, and I'll make like a connection with quantum computation. So this is the only slides I have for today. So let's go to the board. So I stopped last section. I found the energized state for the single harmonic oscillator, right? So let's put here. Continuation. So I stop here. I found the energy for the harmonic oscillator. Like that, we use this Hamiltonian is square plus, I think was this, yeah, square x square. This is the Hamiltonian that we was considering, and the kinetic part, and this is the potential part. And we find the energy associated. H bar omega n plus f. Okay, where n it's discrete 1, 2, 3, 4, and so on. Okay, and we have the ground state, the system that energy is 0 when n is 0, which is h bar omega over 2. This is the energy for the ground state, the harmonic oscillator. And what else? Let's see. Another important thing, we have found like the operator, the annihilator and creation operators also. So we found that A, this operator A, when applied to the state n, it is just n minus 1. And that's why it's called like the annihilation operator. Operator, because since you are in a state, and the next state when applied is always one down. But this is stopped in the ground state, right? Because when n is 0, so this would be 0 times this one. And a dagger is called the creation operator that we show. It's like this. Period. So this was in the last lecture. Just putting the things here. But I stop here, right? I stop. That's the part that I stop. Found the energize. So the thing that's missing, we didn't have time like the last, was to show that we can apply this successively, this creation operator. So let's start today. What's happened when applying applies to P, right? A dagger successively to the ground state. To the ground state. That's this stage 0. So okay, we just need to do is apply this formula here that we show like last lecture. So if we apply this to the ground state, we will have that this will be n plus 1, n is 0, so it will be 1 state 1. Okay, and doing this like successively, like apply again here a dagger square. 0 is the same that apply a dagger to 1, which will give us square root of 2, which means that the state 2 is just a dagger square 0 divided by square root of 2. We can do this like again, a dagger to the cube would be a dagger applied to this guy here, so the square root of 2, a dagger applied to 2, will give us a square root of 2, and because of this, 2 will be a square root of 2 plus 1, so it will be square root of 3. It will be 2 times 3, right? Be 6. Okay? Square root of 6. Three. And so the state 3 will be a dagger 3 applied to 0 divided by square root 6. You can keep going this. You find this expression here will be something n is a dagger of n is square root of n factorial. Because 6 is 3 factorial and 2 is 2 factorial, right? Applied to 0. So this is the relation of a state n with the ground state oscillating. So okay, so in this way, we have succeed in constructing simultaneous eigencats of n. Remember, n was defined as dagger a, and the Hamiltonian age that is defined before with eigenvalues. So the eigenvalues is the energy, right? Is n plus 1/2 h bar omega. If n 0, 1, 2, 3. Okay, this was the only thing I missed in last lecture. So we can use like this, the things that we found from an minus 1 and a dagger n square root n plus 1. So we can use like the orthonormality condition and find like the matrix associated. So from this and the orthonormality condition for the states and the set of states, and we obtain the following matrix element. So when I applied like a state different from n, let's say n prime to an, these would be just like the eigenvalue n prime n minus 1, which is square root of n, and this is like a delta of Kronecker, right? N minus 1. And this, and this. And prime, so now applied to this other term, a dagger n, will be just n plus 1. Again, and a prime n plus 1. This is delta n prime n plus 1. Okay, so this delta here is the just to observation delta ij is equal to 1, if I is equal to j, and 0 if I is equal to j. So these matrix elements for A and dagger are not diagonal, right? The diagonal is always 0, right? Okay, but using this, we can find like the representation for the position and the momentum, and then we can find like the eigenfunctions. We can find like the wave functions psi for the harmonic oscillator. And then we stop like the quantum mechanics part and go to the quantum computing. So okay, so using this, together with the definition, I think there is a question, or I heard something.
Yeah, Berend was asking, do you mean the diagonal is the non-diagonal is 0?
The non-diagonal
of the Kronecker delta.
Here, yeah, here, what? See. And the diagonal is 0, right? Because here, let's say, delta n prime, if n prime is 1, and n is 1, so this would be 1, 0. Which is, oh, okay, you are right. So this would be out of diagonal terms, okay, yeah. Out of diagonal terms is 0. Okay? Because if this is 1, this is 1, we will have delta d1 and 0. So the term, this term here in the matrix.
Yeah, good catch.
This term here is 0, 0, 0. And this is 1, will be 1. Oh, no. Wait. The matrix is this one, okay? So this is 0 and this is 0. So the diagonal term, this will be 0 because this will be 0 and like minus 1. Okay? So if this guy is 1 and this is 1, the delta will be 1 and 0. So the 1 term is this here, will be 0.
One if they're the same, 0 otherwise.
Yeah, it's 0 in the diagonal. Okay. Okay, Barren?
Yeah, I'm still not sure, because normally the general definition is that the diagonal, the way you put it there, I equals J, that means the identical entries are in the diagonal normally. So the way,
but this guy is diagonal. This guy is diagonal. If you do this, this is diagonal. Because this will be like n. When this is applied, it will be n minus 1 times a constant. N minus 1. Okay? But then we apply to this, will be n, because this will up, you sum 1. So this will be a delta n, n. And then this will be like diagonal. I mean, the diagonal will be non-zero. It will be 1. I mean, be 1 times a constant here that this will be square root of n. And yeah, will be n here. That's the number operator. The matrix for the ij for this guy will be like n and outside 0. Okay. You can check this after, okay? But I think is
Okay.
The non-operator, the diagonal terms are always n. But this guy is alone. You can check this in the end. So, using this together with the definition of A and a dagger. So just to remind here, I'll put again the definition we did in last week, the last lecture. A was defined in this way. And omega x plus IP dagger 1 square root 2 mh bar omega m omega x minus IP. So we can see from this, let's use this space, a dagger, a plus a dagger will be just sum this will be m omega over 2h bar times 2x n a minus a dagger minus a will be minus 2 I p square root 2 m h bar omega. And then we find that x is just h bar 2m omega sorry for the things. Let me write again. A x x is equal to h bar 2m omega. I just inverted this equation. A plus a dagger and p is equal to I square root of m h bar omega over 2 times h dagger minus 8. And then we find the matrix for x and p. We define matrix elements of x and p operators. So we do this bra x n and apply to this guy here. We'll find using the things we find above will be like this constant 2m omega and the n prime n from this guy here. I'll put just the result in terms of the delta n prime n minus 1 plus n minus 1 delta n prime n minus 1. So this is n, and this for the same for p. Will be n prime p, and the constant, just repeat, m h bar omega over 2, and using the definition of the deltas. So let's repeat this. N prime n plus 1 minus, because there's minus here, square root of n to the prime and minus. Okay, so x and p are diagonal, right? Not diagonal. So notice that, right, not diagonal, because it's the same. Neither x and p is diagonal, in the n representation. We are using. And this is because x and p do not commute with n, right? We saw this last. We saw this in the last lecture. Because x and p do not commute with n. So, okay, so we can check this in the end, okay, but I think here, because this is 1 and this is 1, this term will be 1 and 2. So the diagonal, this is with 0. And this will be 1 and 0, so it's 0, 2. Okay? But we can check like in the end if you still have any doubt. But and we can also use this to compute the energy eigenfunctions. Functions in the position space. So we still don't have the size, like the wave functions. So to do this, let's start with the ground state. So we know that A applied to 0, the ground state, this is 0. So in terms of X representation, X prime A0. So I'll use the definition of A, okay? That I put in the beginning. This is 1 square root 2m h bar omega m omega x plus IP 0. Okay, this is just the definition of A in terms of X and Y. And we know because of that this guy here is 0. Okay. Okay, so now this is just a number, a constant. So this will be 1 x prime A0. We'll have 1 square root 2m h bar omega m omega x prime x0 plus P, just to remember, P is equal h bar I. We are considering in one dimension, okay? So this d dx. If it's in 3 dimension, this will be a gradient. But because we are considering just one dimension, so I'll write this way. So when I write this I here goes away with this I here. So we'll have only h bar x prime d dx 0. Okay. and this is equal to 0. Okay, so these will have, I don't need this because this is 0. I don't need this anymore, okay? Just don't need to write this. So this goes away when it goes to this side. So I'll have m omega. So x, I can apply x for the bra x prime because it's real. So it will be just x applied to x prime. That's the bra. It will be just x prime. Plus h bar, and I can apply d dx to the bra x prime. This will give me only d dx prime. This multiplied by x prime 0. Okay, is equal to 0. But just to remember, x prime 0, this is just my wave function. This is in the direct notation, but this is the definition of the wave function. So there's 0 to x prime. Okay, remember this is, I think, in the Maria lecture she showed this in the math tools. So okay, I can just to write this, simplify this expression. This thing here will be x prime plus h bar m omega d dx prime applied to the side 0 of x prime. This is equal to 0. And I will define here to write this thing. I will define here x0 is this h bar m omega. Okay. So with this definition, I will write this here as x0 square. Okay, x0 is just the definition. Okay, so we have an equation. Can I have an equation of this type? X0 square d dx prime psi 0 of x prime is minus x prime psi 0 x prime. So this equation is simple, right? Because this will have just psi minus x0 to the minus 2 integral x prime dx prime. Okay, and the result will be psi 0 of x prime, a constant exponential minus x prime square x0 square over 2. 2 here, because when you integrate this will be x prime square over 2. So this is the psi 0. We need to still normalize. So to find the constant a, we have like this is psi 0 square. The x prime square is equal to 1. Okay, this I'll do a little bit quicker, but because we solved it in the past, right? You know, the examples I show more with more details. So the only thing we need to do here is this integration. So we will find that c will be something like square root of 2 pi 1 over 4 x 0. Okay, this integral is you can find in tables. Okay, so with the constant, we find that psi 0 x prime will be just 1 over pi 1 to the 4th square root of x 0 exponential minus x prime square over 2x 0 square. So this is the psi 0. This is for the ground state. This is for the ground state. I think we need to do the things quicker. So we can do the same thing for the other states. So we can obtain the energy eigenfunctions for excited states. For the excited states. Okay. So just defining, right, this for this state x prime 1. This is psi 1 x prime, which is just x prime. One state is just a dagger 0. Okay, this is the one state. And using the definition of a dagger, I will just write here 2 mh bar omega x prime m omega x minus ip 0. Okay, doing the same procedure as before. So this will have psi 1. So again, I'll have like the bra of x prime with x and 0. The same procedure as we did for the ground state. So I'll just put here the answer. Okay. 1 square root of 2 x 0 x prime minus x 0 square dx prime psi 0 of x prime. Okay, because when I do the bracket here in the x, I will have the x prime, and psi 0 would appear, and again here in the p, when I use the definition of p, I'll have ddx and psi 0 there. Just to remember that psi 0 of x prime is this. So the psi 1 will be this expression here, x prime minus x0 square, the derivative, the first derivative from this guy here. And we can keep like doing the same thing, like x prime 2 is just, this is the definition of psi. Psi 2 x prime, which is x prime a dagger square 0, and this is just use the definition of a dagger. This will be just 2 square root of 2 mh bar omega x prime m omega x minus ip square. And then, I mean, I'm not doing it again. This will have psi 2 1 square root of 2 factorial, which is 2, 1 over square x prime minus x0 square dx prime square psi 0 of x prime. And in general, we will find, in general, for psi n, we will find that psi n is equal to 1 pi (1 over 4) square root. I think I forgot a pi here somewhere. That's okay. 2n factorial 1 x0 n plus 1/2 x prime minus x0 square dx prime to the n exponential, that's the psi 0, exponential minus 1 over 2 x prime x0 square. Okay, this is in general. Yeah, this pi over 1 over 4 comes from the psi 0. That's right. So this is the psi in general, and you have like a plot from this psi over x. You have a plot in the Nielsen-Schwenk book, okay? So the plot will not be so important to us now, so I'll not like draw here, not good to drawing things, but you guys can check. The first 5 solutions, you can check. The first 5 solutions of psi in page 285, Nielsen-Schwenk. Sure. Okay, it's better than I come here to drawing something. And will not be important for the rest of the things. So okay, still have a lot of things. So these wave functions, this wave functions describe the probability amplitude that a particle in the single harmonic oscillator will be found. At different positions within the potential. Okay. So, in general, we will be more interested in the following properties of the states. So, the commutator of A and A dagger, this will be, if we, the age and A dagger. So, using the definition of the Hamiltonian, the harmonic oscillator, which is this, dagger A plus 1/2, A dagger use this. This is just a constant, okay? So they can go outside the commutator. The commutator of A. So this first term with this term. So A dagger A dagger plus H/2, the commutator of 1 A dagger. This is, of course, is 0 because this is just a number or the identity matrix. And this is the commutator of A dagger A dagger. So when I have a thing like two operators like here, the rule is just put this H bar omega outside. So this will have like the commutator, the first operator outside, A dagger, A dagger, plus the commutator of A dagger, A. Okay, I don't remember if we saw this in the math tools. But if not, you guys can check like in the coin book. And today I didn't put the page just because I forgot to put the page here, but I can give after that. But I mean, this is the rule. The rule when you have like commutators, two commutators or two operators, more than two operators inside the one commutator thing. So the commutator of A dagger with A dagger, of course, is 0 because it commutes with itself. And the commutator of A and A dagger, we proved this last. This is 1. So this will be just A dagger. And you can apply this to psi. Applying this to the cat psi, we will find that H A dagger psi. We can write this as H A dagger plus A dagger H. Okay, use the definition of the commutator. You can write this way. Psi. This will be just like this commutator here. Here's the answer. So H bar omega A dagger plus A dagger H psi. But remember that H applied to psi is just H applied to psi is always the energy of the system. Psi. So H A dagger psi is just H bar omega plus E A dagger psi. And this is state here, this guy here, is an eigenstate of the Hamiltonian with energy, which is the eigenvalue, this guy, E plus H bar omega. And similarly, A psi is an eigenstate with energy E minus H bar omega. This will be basically the same thing. So I'll put as a homework. Show this, okay? And with this, it follows that a dagger to the n psi are eigenstates for any n with eigen n with integer. E when applied n times, so plus n h bar omega. Okay. This is also like a homework. When apply this like n time, we show for 1, that is this. This is for n equal to 1. So it's simple, it's just following this. Where this E here, where E is equal 1 h bar omega is the ground state, is the ground state energy. Which is the expression we found before, right? So En can be written as E plus NH bar omega. So, okay. Okay, and this will be useful, like not today, but in the other models. A lot of the things that we use here will be important. So this is the quantum mechanics part. And don't worry about the time. This is the quantum mechanics part. I think I finished now. I can like make the relation with the quantum computation. But I don't know about you guys. So what do you think about the time? I don't know. I think I still have material here. I don't know if you guys are tired. So what do you think? I should continue it today, or I could stop and maybe do recording, something like that? What you guys think? You guys that watching live. Because I think at least 30 minutes I still have things. I don't know about. I could stop like now and then record something like maybe tomorrow, or I should continue with this today and finish. What you guys prefer? Don't prefer.
Either way for me.
Yeah, so I'll continue. Okay, if you guys get too tired, I could like stop and continue. Like I can record it. Okay, let's see the quantum computation part. So this is quantum mechanics so far, and we'll use a lot of these things that we learned today. Not only from this lecture, but for the other type of of quantum computing models. So let's see here. I'll try to be quick. So suppose we want to perform computation with this single harmonic oscillator described before. So what can be done? That's the thing. What can be done? Well, we can like choose the representation, at least the usual. I first tried to be like the representation for qubits would be this energy eigenstates. So each energy, each eigenvalues, sorry, the energy eigenvalues. So in fact, like the states, right? Because the qubits is the state 0, 1. Okay. So the qubits could be like the states 0, 1, 2, and so on. But we also need to perform like unitary operations. And one example that you can use here is using like the C0 gate. So let's write these things in. So a natural choice for qubits representation are the energy eigenstates. We call N. Okay, this guy is here. But we also need to perform like unitary operators. So the choice right this way. Let's perform, for instance, C0 gate. In the following way. So let's recall here the C0 gate. I don't know if recall that C0 gate performs the mapping. Just to remember here, the C0 gate, when applied to, let's say, C0 gate is applied to 2 qubits, right? So when applied to something like this, 0, 0, where this is the target qubit, and the other is the control. And just to, I'll use like the distance shrink notation. He's using, in this case here, L here, just to say that this is the logic qubits, not the qubits for the oscillator. Just like remember. So when I have a C0 applied to a system like that, to a cat like that, this will not change. It will be the same, right? So every time the control is 0, it never change my cats. So C0 applied to 0, 1. The logic gate, this is still 0, 1. C0, but when the control is 1, so it change. You have the sum in the target. So when the control is this, the control never change, right? So it's still 1. And here will be the sum of 1 and 0, 1. A binary sum. And C0 applied to 1, 1. This will have 1 and now 0. Okay? Just to don't be confused, this thing here is the logical states. Logical states. And this here is the simple harmonic oscillator states. Okay, just this thing here, just to remember, remind the how the C0 happens. So we have basically a C0 applied for this one. It's the same. This one is the same. This is the same. So you need something similar in the case of the oscillator. So for this simple harmonic oscillator, quantum computer model, we need similar logic to represent a C0 gate. Okay, so suppose that at t equal to 0, the system is started in a state spanned by the single harmonic oscillator base states, which is our M. Okay. And then we evolve the system forward in time. But at each time of the order t pi over omega. Okay, we see why this in instance. So t, where the omega is the frequency of the oscillator. So we know from the Schrödinger equation time evolution of the eigenstates is given by, just write here the Schrödinger equation for time evolution psi of t is just the Hamiltonian psi of t. And because in this case our Hamiltonian is not time dependent, we can have just the solution. This will be just something the exponential, right? So psi will be, I'll not show the details. You can, psi of t is just exponential minus ht h bar t. And we can write like the total psi of tx. You have just this part minus I h t h bar. I showed this with more details, I think 2 or 3 lectures ago. So will be the psi of t equal to 0 x. Okay, this is just the time part, time dependent part, and the time independent part, the initial part. And the psi, this thing here, the psi 0, we can write like the things that we found, right? We can write like as the superposition Cn at time equal to 0, the ends that we found. Okay. Okay, so let's just simplify here the notation. So psi of t, let's write this, psi of t is just this part, exponential minus I h t h bar psi of 0. Right, but and this guy here is just the time evolution operator. Okay, this is t, which is unitary. So to perform quantum computation, you need unitary operations, right? So this is what you can like choose, at least for this example. So time evolution operator, which is unitary. So using this, the things that we found in the quantum mechanical parts, this part here, we will have psi of t would be the sum of n Cn exponential minus I h t over h by n. Okay, just use this guy here. And the Hamiltonian H for the oscillator is just this in terms of the creation and annihilation operator that we just found. So psi of t is just the sum of n Cn, the constant, exponential minus I h bar omega I dagger plus 1/2 t divided by h bar times n. So this h bar here with this goes. Okay, this guy and this guy. And we'll have, this is the sum of n Cn exponential minus I omega t over 2 exponential minus I a dagger a omega t n. Okay, so this for each time t, this will be just like a constant. Okay, so I can simplify this expression, write like psi of t is the sum of n Cn of t. I will put this thing here inside the now I have a Cn of t exponential minus I a dagger a omega t applied to n. Okay, this is my wave function which evolve with time. But what is important for us here is just this part, right? This will be always a constant. So what is important for us is that the single harmonic oscillator energy eigenstates undergo transformations of the type So the important is this part here. This is will give us transformation. Here is my operator, number operator. So n will evolve with this minus I omega t a dagger n. This is the time, and it evolves with time in this way. T. And that's why we choose the system. So the system evolves forward in time by like intervals of t equal to pi over omega. So intervals of t of this type, n is mapped by minus I, so omega and omega goes out, will be dagger a pi n. And now you use the definition of exponential of operator. So using the definition of the exponential operator, just right here, but you guys can check. You can find even like Wikipedia as n equal to 0 to infinity. A is a operator, right? A to the n over n. So this will be like the identity plus a squared over 2 factorial plus a to the n over n factorial. Okay? So using this definition here, in this last term, so we'll find that n evolves in time as like identity minus I pi a dagger a plus the other terms applied to n. So we can check like this is the definition of the n operator. In fact, so we can see that this will be just like 1 minus I pi, and this applied to n is just the n, small n, and plus the other terms, n. And this will be just like the exponential of minus I pi n applied to n. Okay? So this is like n evolves in time with that step with period of times of pi over omega, where omega is the frequency. And we can still simplify this. We can like write this is just the cosine n pi minus I sine n pi applied to n. This is 0 because n is integer 0, 1, 2, 3. So integer of pi, this guy is 0, and this guy can be plus minus 1. And I can write this. So n is minus 1 to the n. Okay? So when n is even, is positive, and when it's odd, is negative. Okay, so the harmonic, the simple harmonic oscillator as a quantum computing we can see like the state 0 goes to 0, is mapped as 0. The state 1, it changed the sign, it's minus the state 1. And the same for the state 2 is 2. The state 3 is minus 3. The 4 is 4, and so on. Okay? So the idea for the C0 gate will be use this. So the C0 gate for this simple harmonic oscillator would be represented by so the idea, we know that C0, so this is for the logic, C0 applied to the logic states, we know it doesn't change. So the equivalent here for the state like that would be like the 0 state, n equal to 0, because it's the time evolution will be always be 0, right? Never change. So let's put here, since this state 0 never change. It doesn't mean if n is odd or even. Never. And okay, but the system, so this is, let's say, the same thing for this guy here. It will always be 0 with 1, right? Every time that the control is 0, it never change these cats here. So the equivalent could not be 1 because 1 change with time, change the sign, the eigenvalues. So the next would be like 2. So 2 would have the same logic of this guy. Since the same. Since 2 never change. Never changes. Okay, but I need something that C0 applied to 1, 0 and C0 applied to 1, 1 in the logic computational basis. The thing that this guy here will become like this, right? And this will become this when you apply the C0. So I need something similar to harmonic oscillator. And something similar here will be a superposition of the states. Let's say this and this. square root because this must be 1, the total probability. So this minus this. Since we can see here, 4 never change because it's even, right? So this eigenvalue here will be always 1. But this eigenvalue will evolve each time. With this, sometimes this will be -1, and then +1 again. But if it's when it's this eigenvalue here is -1, it means that this guy here becomes this. And the same thing here. When this minus here becomes +1, it's evolving in time. This minus will be plus, and this guy here now is this. So, because 4 never changes. When I say never change the eigenvalues. Huh? It's always +1, and 1 goes to -1, -1. After t time interval of pi over omega. So these guys change. So this states here, the superposition of the state here become this, and this vice versa. So the result of these states, and what I call here 1 to 4, right? 1. Results. Now the result of this state is the desired CNOT gate transformation. And what is doing the whole of the CNOT gate is the time evolution. This is the time is evolving. Okay, so this is the idea. So in general, to know the time, I think it's a necessary condition for a physical system to be able to perform unitary transforms, which is necessary, right, for quantum computation. Transform is simple. The time evolution operator for the system. Which we use, in this case, t, h is the exponential of minus I h t. If h is the Hamiltonian, and t is the period of time that we are doing the computation. So in the case above, the C0 gates was simple to implement because it only has eigenvalues plus and minus 1. Plus and minus 1. Okay, so I think it's too long. I mean, still have some, but small comments. Like, I suggest that you guys maybe should read a little bit the drawbacks, because otherwise I will take too much time. I will just make the summary here. Okay. And then we can, when we return, we can discuss the doubts that you guys could have. So the summary for this simple harmonic oscillator quantum computer. Like the qubit representation. Adjust the energy levels. Like 0, 1, and so on, right? Unitary evolution, just the time evolution related with the time operator related with the Hamiltonian. Unitary evolution. And just arbitrary transforms. In this case of T, the time operator, realizing by matching the eigenvalues spectrums to that given by the Hamiltonian. In this case, the part that's necessary is the associated to A dagger A, which is the N operator, right? The number operator. So this is the summary. We didn't give any initial state preparation. It's not discussed in the book, not considered. And the readout, like the output, is not considered as well. Not considered. Because this is just like a theoretical model. So we see and you still have the drawbacks, but I didn't have time like to comment because it take too long. But you guys like can like see the Nielsen Schwenk arguments, and when we return next year, we can like discuss. So I think I'll finish here for today. Okay, because I mean it's almost 2 hours. So this will be the last lecture for this year, because the next topic I'll talk about the quantum oscillator, the photon quantum computing. So the things that we use here will be very important for apply when we're doing in more realistic systems, like in the next topic. But because like is the type of topic I would start. If I start next Friday, we would return just in January, so it will be like a gap. And I think it's important. Maybe we stop here, return in January. I still don't know the date, but probably I think the 5, January the 5. I don't know. It will depend of you guys. But this intervals is almost like 20 days. It's important to you guys to review the things that we saw so far, that you guys review. So in the first lecture in the next year, we can like discuss if you guys has any doubt. So I'll stop here. You guys has any questions? So I will stop the video because I think it would be too large. Okay, stop the presentation.
Yeah, thank you very much, Carlos. It was really interesting, but I think I have to digest it first, and that will be the meal for Christmas.
Yeah. So okay, so I'll stop the recording now. So people in YouTube that cannot watch live, like have a good, very nice, very good Christmas and New Year. So okay.